Hello, everyone. Before I begin the lecture, let me do a little bit about the schedule. So earlier this week, the quiz for the material for exam 2 went up. That is still open, so you can take that at any time. The Dropbox for homework 2 has gone up, so you can also start turning that in. And the exam 2, opened up this morning. And you can start working on it, and it's due by the end of the day, Sunday. I mentioned in the midterm grade video that I'm not going to be assigning a paper this semester. There's just so much going on, and usually what we want you to do in the paper is to go to the library, but that's kind of something I can't really ask you to do in the middle of a pandemic. And you'll see that there's a video where I talk about midterm grades. So make sure to check that out, as midterm grades were put up earlier this week, not later this week. That doesn't make any sense. Midterm grades were put up earlier this week. So before I begin the lecture, or at least my part of the lecture, I want to show you a video on the connections between work, potential energy, and kinetic energy.
I have here.
So you saw there at the end the name of the video if you want to look that up on YouTube. The whole point of that video was to relate work with potential energy. He actually mentioned he gave the object potential energy by doing work, but the amount of work he did was mgh. I mentioned I mentioned two work formulas in class earlier this week, last week. One of them was work is equal to force times distance. That's if you're given force. The other is work is equal to mass times the acceleration of gravity times distance if you're given the mass and you're lifting up the object. But mass times the acceleration of gravity times distance is also the potential energy formula. Or at least it would be. We're going to make one small change. Instead of using D, we're going to use H. Why? Because we're talking about a very specific. Give me a moment. Talking about a very specific type of distance. We're talking about the height above the floor. Trying to get rid of some of this glare. Let me switch the lights in here. All right. So the distance that we're trying to deal with here is the height above the floor. So it has a very specific distance in mind for this. And then for kinetic energy, kinetic energy is going to be equal to 1/2 the mass of the object times the square of its velocity. And in that pendulum, the pendulum had a certain amount of potential energy to start out with based on how high he lifted it up. And when he let it go, that potential energy got converted into kinetic energy and then back again as the pendulum started going back up. So let's take a look at how to use these two formulas. And I'm going to start out with the kinetic energy formula. So my first problem says, what is the kinetic energy of an object moving at 100 meters per second if its mass is 20 kilograms? So kinetic energy equal to 1/2 the mass, which is 20 kilograms, times the velocity, which is 100 squared. Half of 20 is 10, and 100 squared is 10,000. So 10 times 10,000 is 100,000. And this is a type of energy, so the units for this is joules. So this comes out to be 100,000 joules. The next problem I'm going to do is another kinetic energy problem. This time it gives me the kinetic energy. It says that I have a 40 kilogram object with a kinetic energy of 1,000 joules. So I have the kinetic energy, I have the mass. What I'm trying to find is the velocity. The first thing I'm going to do, let me multiply 40 times 1/2, which is 20. I need to get the v squared by itself, so I'm going to divide both sides by 20. Cancel it out on that side, and v squared is equal to 1,000 divided by 20, which is 50. But we don't want v squared. We just want plain old v. So v is going to equal to, take the square root of both sides. The square root of v squared is just plain old v. The square root of 50 is 7.1, and this is a velocity, so it's meters squared. This is really the hardest one that we'll have, I think, for this whole section. Because you have to remember that since you have v squared and you want to solve for v, you're going to need to take the square roots at some point. And I've seen a whole bunch of attempts to do this without the square root, and you just can't do it. So since you're trying to solve for v, but this has v squared in it, you're going to have to take the square root. Here's where you take the square root. You've only got v squared on that particular side. Don't try to take the square root earlier. You'll end up with a mess. My last kinetic energy problem, I'm given that the kinetic energy is 3,000 joules. This is problem number 24. And then I have an object that is moving at 10 meters per second. And what it's asking me for is the mass. First thing I need to do is square this 10. That's going to be 100, and I can move it over. And then get 3,000 is equal to 1/2 of 100 is 50. Once I get here, I need to get m by itself, so I'm going to divide both sides by 50. The 50s on this side cancel out. And 3,000 divided by 50 comes out to be 60, and this is a mass, so this is 60 kilograms. All right, now let's take a look at a potential energy formula or two. Number 25. And a good indicator that you're being asked a potential energy problem is that you're holding something. You're holding something above the floor. So you hold an object with a mass of 50 kilograms, a distance of 2 meters above the floor. What is the potential energy? So remember, the potential energy formula is mass, which is 50, times g, which is 9.8, the acceleration of gravity. That number doesn't change. And the height above the floor, which is 2. 50 times 2 is 100 times 9.8. You're going to get 980, and this is an energy, so it is in joules. The hardest part about the potential energy formula is remembering that 9.8 is going to be there even though the number isn't given to you. G will always be 9.8. Problem number 28. A 100 kilogram object has a potential energy of 1,000 joules. What distance is it held above the floor? Okay, so our potential energy here is 1,000. The mass of our object is 100. G is still 9.8. And the thing we're trying to find is the height, h. 9.8 times 100 is 980. I need to get h by itself, so I'm going to divide both sides by 980. And h is going to equal to 1,000 divided by 980, which comes out to be 1.02 meters. The potential energy formula really isn't that difficult to use. Number 27, though, can be kind of difficult. And you have to think about what it's giving you. An object is held 20 meters above the floor. It hits the ground with 3,000 joules of kinetic energy. Assuming the object is dropped in a vacuum, how much potential energy does the object have, and what was the height it was dropped from? So we have a potential energy problem, and they've given us the mass of an object. They haven't given us the potential energy, and it's asking for the height. Except it has given us the potential energy because it's given us the amount of kinetic energy the object hits the floor with. And where did this kinetic energy come from? Well, it came from the amount of potential energy you gave the object based on how high the object is. So notice I'm holding this marker right here above the floor. It has a certain amount of potential energy. At the moment, though, it has no kinetic energy because I haven't let it go. It's not moving. And remember, kinetic energy is the energy of motion. But right now, it's all potential energy and no kinetic energy. But as soon as I let it go, it starts to move. And what is happening is the potential energy is being converted into kinetic energy. Is it all converted at once? No. As long as the object is above the floor, it still has potential energy. It has the amount of potential energy equal to the distance above the floor. So here it has a certain amount of potential energy. It has no kinetic energy because I haven't dropped it. But let's say I have dropped it and it drops to here. Now it still has potential energy because it's above the floor,
But it's also in motion, so it has kinetic energy as well. And then finally, when it hits the floor, it is no distance above the floor, so it no longer has potential energy, but it does have kinetic energy. And how much kinetic energy does it have? It has the same amount of kinetic energy on the floor when it hits as it had potential energy from when I was holding it. The reason I mentioned in a vacuum is that in this room, it doesn't quite work out that way. I drop it, potential energy gets turned into kinetic energy, but it also gets turned into another type of energy, heat, because of the friction of the air that the marker is falling through. And that heat gets spread out into the room, and by the time the marker gets down to the floor, it has a lot of kinetic energy. It has a kinetic energy close to the amount of potential energy it started out with, but it doesn't have the entire potential energy that it had before. It doesn't have as much energy inside of itself as it did at the beginning because it's been losing energy to the air in the form of heat. But in a vacuum, the amount of potential energy I give the marker at the beginning is the amount of kinetic energy it has when it hits the floor. So in this case, the potential energy, actually, let me check, make sure I got that number right. Oh, that's 5,000. The amount of potential energy that the object has is 5,000, which is the amount of kinetic energy it has when it hits the floor. The mass of the object, oh no, I wasn't given the mass, I was given the height. So I'm trying to find the mass of the object. Here's the potential energy. Mass of the object is the thing I'm trying to find, and I'm dropping it from 20 meters height. All right, so I got 5,000 is equal to 20 times 9.8, which is going to be 4,900. Is that right? Am I looking at the wrong problem? Twenty times 9.8. Give me a moment. 20 times 9.8 is not that. It is 490. And let me see then. Let me make sure I have that right. 980 times 10. 98. No, that's. Here's where I need a calculator. $196. Sometimes I can do calculations in the head, sometimes I can't. Okay, so 9.8 times 20 is 196. I need to get m by itself, so I'm going to divide both sides by 196. And if I remember from when I calculated this last, 5,000 divided by 196 should be 25.5. And it is. So I'm given the kinetic energy. I'm given the kinetic energy when the object hits the floor. That's the same as the potential energy from when I dropped it. So kinetic energy is equal to potential energy. I'm trying to find the mass. The gravity is 9.8. The distance I drop it is 20. 9.8 times 20 is 196. I'm going to need to divide both sides by 196 to get this to cancel out and leave me with just m. And then 5,000 divided by 196 is 25.5. Sorry about that. I should have just gone ahead and grabbed my calculator to make sure I had this calculated correctly. Before I move on, I want to show you an application of something that we can do in physics. So since when I have the marker here, and it's nothing but potential energy and no kinetic energy. And when it hits the floor, it's going to be nothing but kinetic energy and no potential energy. That means that sometime during the fall, potential energy will equal to kinetic energy at some point called K. Does it matter what point that is? Actually, no, not for what we're doing. So since it really doesn't matter at what point K is at, where K is just some height on the above the floor between where I drop the marker from and the floor. Since that doesn't matter, I can set these two equal to each other, and then I can set their equation equal to each other. So MGH is equal to 1/2 mv squared. MGH being the formula for potential energy and 1/2 mv squared being the formula for kinetic energy. I see mass on both sides, so I'm going to divide this side by m. And if I do it over there, I need to divide this side by m. Notice I did it over here to get them to cancel, but they cancel over here as well. Now that gives me g, which I'm going to rewrite as 9.8, but remember g is the acceleration of gravity on Earth, 9.8. And over here I have 1/2 v squared. I'm going to multiply both sides by 2. That's going to get rid of the half. 2 times 1/2 is just 1. And 2 times 9.8 is 19.6. I now have v squared is equal to 19.6h. I take the square root of both sides. What I get is this formula right here. The velocity is equal to 19.6h. This formula does the exact same thing as some formulas did back in the previous set of work. So when I gave you that list of 10 formulas before the first exam, there were some formulas that does the exact same thing as this does. This just does it better. What this tells me is, if I know how far an object has fallen, I can plug that in for h, and it will tell me what the velocity of that object is at that point in time. So let's say I drop this marker from a height of 2 meters, and I want to know how fast it's going when it hits the floor. I'll just plug in that 2 meters, do this formula, and it will give me the velocity at that point. But let's say I don't care the velocity when it hits the floor. Let's say I only care about the velocity when it's fallen 1 meter, whether or not it hits the floor or not. And I just plug in the distance it's already fallen, and it will give me the velocity at that point. And this, it doesn't really matter from how far I've dropped it. The only thing that matters is how far the object has fallen. And I don't have to wait until it's done falling. I can get the velocity at any point during the fall. All I need to know is how far the object has fallen. So this is a nice formula to have. You should add it to your notes. But at the same time, the big thing I want you to notice is I took one formula and another formula, and from those two formulas and a little bit of understanding of how those two formulas are related, I was able to derive a new formula. And a lot of the formulas in physics that we have are derived from other formulas from physics. So if you ever get a question on, can you derive new formulas from old formulas, the answer is yes. Okay, we have two more problems, and they have to do with power. We have two different power equations. One is for kinetic energy. The other, the one that we're going to be using in the homework, is for work. What power is, it's how much energy you're using in a given amount of time, so how fast you're using energy. So we have a formula for kinetic energy where it's power is equal to kinetic energy divided by time. The kinetic energy is in joules, the time is in seconds. We have power is equal to work divided by time, where work is a type of energy. Work is in joules, times in seconds. We do not have a similar formula for potential energy because remember, potential energy is the energy of the object is just sitting there. It's not changing over time. It's just, here's the potential energy. Well, it's still sitting there. It's still the same potential energy. It doesn't change no matter how much time you wait until you finally drop the thing. And then at that point, you're more interested in kinetic energy anyway. I said for the homework, we're going to be using this formula right here. Power is equal to work divided by time. But the power formula for kinetic energy basically works the exact same way. You're just given a number and told, well, this is kinetic energy. Or you have to, or you're given information to calculate the kinetic energy. But once you have the kinetic energy, you plug it in the same way as you would with work in this formula. So number 28. You lift an object with 1,000 newtons of force, a distance of 5 meters in 10 seconds. How much work did you do? And how much power did you use? We're going to have two work formulas. One that has force in it. W is equal to F times D. Work is equal to force times the distance you move the object. The other has mass in it. So W is equal to, let me change that. W is equal to the mass of the object times the acceleration of gravity times distance. This is when you're lifting an object and you're told the mass. This is when you're lifting or moving an object and you're told the force. Well, in problem number 28, we're told the force. We're going to be using this formula right here to find work. So the force is 1,000 newtons times a distance of 5 meters. The amount of work you did here is 5,000 joules. We're then going to plug that into this formula. Power is equal to work, which is 5,000, divided by time, which was 10 seconds. So 5,000 divided by 10 is 500. And the units for power is watts. Finally, number 29. You lift a 1,000 kilogram object a distance of 5 meters in 10 seconds. So it has the same numbers as the previous question. The difference is that the value it gives you is not a force, it's a mass. So we're going to be using this formula here to figure out work. Work is equal to a mass of 1,000 times gravity, which is 9.8, times the distance, which is 5. So I got 1,000 times 5 is 5,000, times 9.8 should be 49,000 joules. Now we want to find the power. The power is 49,000 joules of work divided by 10 seconds of time, which comes out to be 4,900 watts. Mostly doing energy formulas like work, potential energy, and kinetic energy aren't that difficult. The hardest one to work with is the kinetic energy one because the velocity is squared. The power formula is easy to use. You just got to make sure that you calculate the kinetic energy if you're given the kinetic energy correctly, or to use the proper formula to calculate the work correctly if it's asking you for work divided by time. But again, none of these are particularly difficult. And hopefully now you are ready to take this next exam. I will see you next week.